Okay, so first of all, anybody have any questions you'd like me to go over? Homework questions or anything?
At the moment.
Okay. Well, we are now moving on to control volumes. And for now, we're going to do, we're going to use two laws. We'll come back to it later with entropy. But for now, we're going to use conservation of mass. And we'll talk about that most of or all of today, and then we'll get into the first law for control volumes. And again, this control volume analysis is for when you have material coming in and out of a volume. It's hard to track the material. So instead of tracking the material, you're just paying attention to the volume, and then you have to take into account what's coming in and what's going out. Okay, so conservation of mass, or the mass balance. So this just says that the rate of change of mass in the control volume is equal to the rate of mass coming into the control volume minus the rate of mass going out. Makes sense? And if you think of an inlet, so let's say, so here's our tank. And here's where the material is coming in. So it's going this way. So think of this as like a pudding jello-like material that's going into the tank. Okay. Think of the mass of that at a single instant. The mass of this extruded piece if we think of, so A is the cross-sectional area, that would be the area of this window. We'll call this length L. Then the mass is going to be the density times the volume, which is the density times the area times L, right? And so that means the rate at which mass is coming in is the density, because the material is the material, times the area of that window, because that's not changing, times L dot, or I guess I'll write that as dLdt. And that dLdt is just the velocity of the material going through the window. That's rho A V, where V is the flow velocity in. The density we don't use as much as the specific volume. So remember that since density is 1 over the specific volume, we can write this as m dot is equal to A times the speed of the material divided by the specific volume. And that's a formula we're going to use a lot. That's the same as the formula you use to calculate the mass flow rate going out. It's just going the opposite direction. And one thing to remember, you'll see sometimes talking about steady state. So steady state means Dmdt in the control volume is 0. And that's the same as saying the rate of mass flow in is equal to the rate of mass flow out. Okay, so let's do a couple examples with liquid. So first, if you have if a tank can hold 20 kilograms of water, and the mass flow rate going in is 2 kilograms per second. The mass flow rate out is 1.5 kilograms per second. How long until the tank fills? So the mass balance says Dmdt in the control volume is equal to the mass flow rate in, so 2, minus the mass flow rate out, so 1.5. And so all this is equal to 0.5. And now it's just an integration to calculate when that change in mass is going to hit, what did I say, 20 kilograms. Separate variables and integrate. Bless you. And you get that the change in mass is equal to 0.5 dt, 0.5 times the change in t. And so 20 is equal to 0.5 dt. And so dt is equal to 40 seconds. And that's sort of like the simplest form of the way that you'll most often have to use this equation. You'll set it up in that differential form, and then you'll have to integrate to find like a certain change in mass. But usually, instead of being given mass flow rates, you'll be given stuff like the speed of the flow coming in. And sometimes you'll have to use a table to find, properties, find the specific volume, stuff like that. So let's say now that there is, so you have a tank. With an inlet and an outlet. And it's liquid water going in and out. And the whole thing, there's no changes in temperature or anything, 20 degrees Celsius, 1 atmosphere of pressure. So we know that the density of water is 1,000 kilogram per meter squared. The specific volume is 1 times 10 to the minus third meters cubed per kilogram. Let's say that at the inlet, the area of the opening is 0.02 meters squared, and the speed of the water coming in is 3 meters per second. That always has to be an average speed because, as water comes in through a tube or an opening or whatever, at the edges it's moving really slowly, in the middle it's moving faster. So this V is always talking about an average flow rate. And at the outlet, the area is 0.01 meters squared. And the speed at the outlet on average is 4 meters per second. And let's say it starts at 500 kilograms of water in the tank. How long until there's 5,000 kilograms? Okay, well, we have Dmdt for the control volume is equal to the rate of mass flow rate in minus the rate of mass flow rate out. And we can rewrite this since we know the volume, the specific volume, the speed of the liquid, and the area of the aperture. This flow rate in is the area, 0.02, times the speed, 3 meters per second, divided by 1 times 10 to the minus third. That's the specific volume. And at the outlet, there's an area of 0.01 meters squared, a flow rate speed of 4 meters per second, and a specific volume, again, that's 1 times 10 to the minus third. So Dmdt is, I think this is 20. And so you can separate the variables and integrate. This is from state 1 to state 2. This is from state 1 to state 2. So integrating the dm gives you the change in mass in the control volume. And we know that we want that to be 5,000 minus 500. Yes? Okay. 60 for the inlet minus 40 for the outlet, right? Okay. And then, so this is 4,500. That was the change in mass that we're looking for. And that's equal to, 20t or 20 times the change in time. And so what's that? T equals 225, I think, seconds. So about 4 minutes. That was cool. I thought it was in a movie for a second, like a movie about a teacher who overcame his debilitating ankle injury.
Yeah. And made it here only 4 minutes late.
And then talked for 10 minutes about nothing. Okay, so that's the idea. You can also use conservation of mass in systems where there are changes in phase. So these are all liquid and all the properties stay the same, but you could imagine that over the path of this liquid or this material or whatever, the temperature is changing, the pressure is changing, which means the specific volume is changing. So let's do an example where we have water in different phases. So this is including phase changes. So say we have a heater in a power plant, a feed water heater. It's at steady state. And let's say there are 2 inlets and 1 outlet. At inlet 1, it's water vapor coming in. And it's at a pressure of 7 bar, a temperature of 200 degrees Celsius, and a mass flow rate that we know of 40 kilograms per second. At inlet 2, we have liquid water. And we know that the pressure is 7 bar. The temperature is 40 degrees Celsius. The area of the opening is 25 times 10 to the minus fourth meters squared. And then at the exit, we have saturated liquid water. The pressure at the exit is 7 bar. And the volumetric flow rate is 0.06 cubic meters per second. So we're already given the rate of mass coming in at inlet 1, but let's calculate the rate of mass coming in at inlet 2 and going out at the exit. So what are M2 dot, ME dot, and then also what's the volumetric, what's the velocity going in at inlet 2? Okay, well, first, do we have enough information to, so if we're going to calculate the mass flow rate at inlet 2, we need to have the area, the volume, the area, the speed of the material flowing in, and the specific volume, right? We're not given the specific volume, but are we given enough properties that we can look it up in a table? This is just water. It's liquid, it's compressed liquid water. So we need 2 properties to look it up, and we have pressure and temperature, okay? And so we can express everything but the speed, and then hopefully we'll be able to use the mass rate balance equation to calculate the speed. And then what about the saturated liquid water at the exit? Do we have enough information there? We have the volumetric flow rate. Well, if you have the volumetric flow rate, to get the mass flow rate, all you need is the density. And the density is 1 over the specific volume. So again, do we have enough to look up the specific volume in a table for water?
Yes.
Yes, because it's saturated, so all we need is pressure. Yep, exactly. Okay, so first let's do the exit, I guess. That's the easy one. So the mass flow rate at the exit is the density times 0.06, which is 0.06 divided by the specific volume. This is liquid, so the specific volume is going to be somewhere around 1 times 10 to the minus third. But since we have that pressure, we can look it up. It's a pretty high pressure, which means the saturation temperature is pretty high, which means that specific volume is going to be at least a bit higher than 1 times 10 to the minus third. So look in the pressure saturation table for liquid water. and you get a specific volume at the exit that's equal to 1.108 times 10 to the minus third meters cubed per kilogram. And so the mass flow rate at the exit is 0.06 divided by 1.108 times 10 to the minus third. And that is is that 54 or something? 54.15 kilograms per second. And then at the second inlet, we're going to calculate that as the area of the aperture times the speed divided by the specific volume. We can look that up in the compressed liquid water table. At the temperature that's given of 40 degrees Celsius and the pressure that's given of 7 bar. And that is 1.0078 times 10 to the minus third. It's lower because it's a lower temperature.
Quick question.
Yeah.
Do we even need to do this calculation if it's steady state? Can't we just use, now that we have that inlet 1 and exit 1? Shouldn't m.1 plus m.2 equal m.e for steady state?
Yeah, but let's see, we calculated, so we have two of them. So we could calculate the mass flow rate, you're right.
Okay.
Doing that, you're exactly right. But we also want to calculate that speed.
Oh, yeah.
Yeah, so
we do have to go through this.
So yeah, you're right. So yes, we could have done the first part already. So let's go to the, so we have Dmdt for the control volume is equal to m1 dot plus m2 dot minus m exit dot. And it's steady state, so this is 0. And so we can write this as m1 dot plus m2 dot is equal to m exit dot. For 1, we have 40. For 2, we're trying to find that. And then the exit was
54.15.
Yep, 54.15. And so the mass flow rate at the inlet 2 is 14.15 kilograms per second. And then once we have that, we can use that to calculate the speed. So these two together A2 times the speed 2 divided by the specific volume at 2 is equal to, the area was 25 times 10 to the minus fourth. The specific volume was 1.0078 times 10 to the minus third. We don't know the speed. And that's equal to 14.15 kilograms per second. And so now you can solve for V2, and you get that speed is, I have 5.705 meters per second.
Yep, that's exactly the same.
Any questions about that? Okay, well, I guess that's the end of mass rate balance. So let's talk about the first law of thermodynamics. This is the bigger one. So the first law for control volumes. So previously, the first law was basically the time rate of change of energy in the system of system energy is equal to the heat added to the system, we're doing differential. So the rate of heat transfer into the system minus the rate of work done by the system. So now we have to deal with the fact that energy comes in and out with the material as the material moves in and out. So now we have to change to a form like this. We still have the time rate of change of system energy. Let's say this time we'll call it the time rate of change of energy in the control volume. Is equal to the rate of heat transfer into the control volume minus the rate of work done by the control volume plus the energy carried in at the inlet minus the energy carried out at the exit. And these are both rates. Okay, so let's start thinking about what this would add to the differential first law. So you have the time rate of change of energy in the control volume is equal to Q dot minus W dot plus at the inlet, if you take all of the terms that make up the energy in the material, there's an internal energy, there's a potential energy, a kinetic energy, and then there's also, you know what, let me erase this, but I'll get back to this in a second. So the energy that's carried in, the energy in the material that's coming in, we have m dot times the specific internal energy. We have the rate of change of potential energy. So that's m dot times g times h. We have the kinetic energy of that material, so 1/2 times m dot times the speed squared. And then we also have the work that's done by the material that's pushing its way into that inlet. Okay, so if you have like, let me see. If this is your inlet, okay, this material is applying a force this way, and the rate of work that it does is that force times the velocity, because remember, work is equal to the force dotted with the displacement. So this is just the rate of change of that work, the rate at which that work is being done.
The power going in?
Yeah. And that force is equal to the pressure in the material times the area. And we can rewrite this. It's a little bit of a sort of sleight of hand, but you can come up with this expression that says AV can be rewritten as m dot times the specific volume. And so you can rewrite this work, this rate of work, as m dot times PV. Okay, so now the rate of energy coming in at the inlet is the mass rate times the specific internal energy plus the mass rate times GH plus 1/2 times the mass rate times the speed squared plus the mass rate times PV. And if you put all that together, it gives you the time rate of change of the energy in the control volume is equal to Q dot minus the work done, the rate of work done by the control volume, plus m dot times the quantity, U at the inlet, specific internal energy, plus P times V at the inlet. That's from that work that we just calculated that's done by the material pushing its way in, plus the kinetic energy term, speed squared over 2, plus G times the height. Since we're already calling enthalpy H, I'm going to call this Z. The same exact thing happens at the exit, except we're subtracting that. So, and I didn't put an I on the mass flow rate, but that's the mass flow rate at the inlet. The mass flow rate at the exit is m dot sub E, and you have all these same terms. So the specific internal energy at the exit plus PI times specific volume at the exit plus the speed at the exit over 2 squared, speed squared over 2, plus G times Z at the exit. And there's one more simplification now we can make. So notice that it was this work that's done by the material pushing its way in at the inlet and pushing its way out at the exit that gave us these PV terms here.
Yeah.
And so now we can call this specific internal energy plus P times V the specific enthalpy. And that's where the enthalpy.
But what's the difference then with the other work term, the W control volume? Is that
Yeah. So this is the work done just at the inlet and exit by the material pushing on the other material as it comes in.
But that could be anything else going on?
The work is if the control volume itself is expanding or something. Say the control volume itself is a piston.
Oh,
you know.
Okay. Gotcha.
Yeah. So this is now the enthalpy at the inlet. This is the enthalpy at the exit. And that's where that enthalpy thing becomes a thing at all, is because it's useful in this application. So I'll rewrite this. This is the final form. The change of energy in the control volume with time is equal to Q dot, the heat coming in, minus the work done by the control volume, plus the mass flow rate at the inlet times the quantity, specific enthalpy at the inlet, plus the speed at the inlet squared over 2 plus gz at the inlet minus the mass flow rate at the exit times the quantity specific enthalpy at the exit plus the speed at the exit squared over 2 plus g times z at the exit. So that's the final full form of the first law for control volumes. So this is, pretty ugly. There's a lot going on there, but when we use it, almost always some stuff is going to go away. So some terms almost always disappear. So now I want to go through just sort of what things to look for so you can cancel the terms in this equation. Okay, so first of all, if it's steady state, then the rate of change of energy in the control volume is 0. Okay, now a lot of times the rate of heat into the control volume, so Q dot, is equal to 0 if any of these are true. First, if the control volume is well insulated. Second, if the surface of the control volume has a small area. So if there's a small area, surface area for the control volume. Third, if there's a small temperature difference between the control volume and the surroundings. And the last one, the fourth one, is if the material is moving fast through the control volume. Let's say if it spends little time in the control volume, then it just doesn't have enough time to for conduction to happen. Okay, so if in a problem, if you see any one of these 4 things, those are hints that you can cancel the Q dot. So if a problem says it's a steady state process and the control volume is well insulated, that means you're going to cancel the Dmdt and the Q dot. Next, the work done by the control volume is equal to 0 if all of these things are true. So for the heat, notice we only needed one of the things in these lists to be true. All 4 of these things have to be true, 3 of these things, for W dot to be 0. First, no displacement of the control volume boundaries. So that eliminates things like a piston, you know. Second, no rotating shafts. And third, no electrical work. And then the last ones are kinetic energy and potential energy. These are almost always going to be small, negligible compared to the other energy terms. So these are usually small compared to the other terms. So they can usually be ignored. I guess the one notable example I can think of where you don't ignore the potential energy is we'll talk about pumps, like pumping water up a certain distance or whatever, and then you have to, the potential energy of the water at its higher point is important. But throughout this class, almost always the height change of the material and the speed change of the material is not going to be important, or the speed change can in other ways, but not for kinetic energy. Okay, so so let's see, what are we going to talk about? So we're going to talk about, the specific devices that we'll discuss. Are nozzles and diffusers, turbines, compressors and pumps, that might be all. I might be forgetting one or two, but one by one, we're going to go through all of these devices. We're going to start with the full differential control volume first law, and we're just going to cross out terms until we get to like a pretty concise, simplified form for all of these, which is just sort of like, so like for a nozzle, we'll be basically, we'll end up with an enthalpy term and a, maybe it's a kinetic energy term there. But I have to stop there because I didn't bring any notes for that stuff. Anybody have any questions about any of this?
Again, just as a refresher for the internal energy,
Yeah.
UI, What forms does that take again? For like the enthalpy term, the U in there?
Yeah. Well, what form? The temperature of the gas, basically.
Oh, okay, yeah.
Yeah, that's basically what it is. But it also can be, if you have a phase change, then it's also the energy of expanding the material.
Okay, yeah.
So that's the thing that's increasing as you go through, like as you keep adding heat to a material to take it from a liquid to a mixture to a gas. Yeah.
Because the Q term in there then would be like, that's for the material going in, right?
The Q is like the heat passing through the walls.
Okay, the walls into the
That's
system.
right.
Or from the material going into the system, or just from the walls into the system?
We're assuming that the material is moving fast enough that that there's no like conduction of heat through the. I suppose convection is.
In certain systems?
Well, yeah, I mean, convection is carrying this stuff in, but I think the inlet and exit terms are dealing with that convection.
Yeah.
So I think you can just think of the heat as nothing but the heat that's passing through the boundary of the control volume.
Got it. Yeah, so just when working on homework problems, getting all my terms straight.
Yeah.
Because that first energy one, I'm like, all right, am I defining, each term and put them on the right side of the equation? What's work side and weak side?
Yeah. Yeah. Any other questions?
Well, I kind of asked the same question
Yeah.
in another class, but this spending little time in the control volume,
Yeah.
is there
A cutoff or
just give me something? I don't have any impression
You know what?
of how much time is usually spent.
I don't either. But for questions that you get out of textbooks or whatever, like just think of that as a clue. You know what I mean? Like, and I don't really have anything more to say about it than that because it really just depends on how much precision you need in your answer, how much time it, you know what I mean? Like if you need a very rough answer, then you probably can ignore the heat transfer, except in kind of extreme cases. If you need a very precise answer, then even if it's moving through pretty quickly, even if the thing is insulated, you have to take it into account, So I think the main worth of that, of having that in mind is just like if you see a problem and it says it moves through fast, it's telling you you can cancel that.
Okay.
Yep. Anything else? Okay. Well, tomorrow I normally have office hours in the morning, but I can't tomorrow. So if you want to talk to me, send me an email and we can set up a Zoom meeting. And yeah, I'll try to get your thing printed. I think we can get it printed by Tuesday. Okay. Have a good weekend. Talk to you later. Yeah. We did a quiz last.
Oh, I didn't know it was every other week.
Oh, I don't know. Yeah, at most it'll be every other week, I would say. Yeah. I'll try to keep telling you on D2L before I give you a quiz, so you glance at the notes. That's right. Yeah.